The block diagram represents the FSK transmitter. Here consider a bit stream. Let it take for example 101. It consists of two oscillators, and both the oscillators will be depending on the bit 1 that is transmitted. So when the 1 is transmitted, the oscillator 1 will be generating a frequency, higher frequency FH, while if 0 is transmitted, it will be inverted to 1 by the inverter. Oscillator 2 will be producing a lower frequency FL. Both the frequencies will be added and FSK output is generated, where first bit 1 will be corresponding to higher frequency and 0 bit will be corresponding to lower frequency. Here we have the FSK modem. It consists of the FSK generator to generate the FSK signal, a pattern generator to give the input stream of bits, a noise generator to generate the noise at the input side, adder to add noise and the FSK signal for getting the distorted FSK signal. Here it consists of the FSK receiver which will give the input data stream back. The first step, it will be consisting of measuring the carrier frequency. First of all, at the transmitter side, the frequency adjustment knob should be at the maximum. Check the FSK output, that will give us the carrier frequency. Here we have the carrier signal with a frequency of 2 kHz and approximately peak-to-peak voltage of 4.5 volt. Here we have the FSK modem. FSK generator is used to generate the FSK signal. Without giving any input, the output is measured to get the carrier frequency. And your pattern generator, we check for the pattern for generating the FSK signal. Here on the DSO, we can see the pattern generated. Here we can see the pattern generated is 10100. We'll check the bit duration, TB, using the cursor. Here we get the bit duration as 3.2 milliseconds, that is approximately 3 milliseconds. The V peak to peak is 5.12 volt and frequency of the entire signal is 100 Hz. Step 3, we'll give the pattern generator output to the data input of FSK generator and check the FSK output and observe it on DSO. Here on the screen we have the bit pattern and the FSK generated signal. So here we can see exactly where the frequency is changing. From bit 1 to bit 0 we have high frequency and lower frequencies. Here the inbuilt circuitry is such that for bit 1 a lower frequency is transmitted, while for bit 0 a higher frequency is transmitted. For the FSK signal, measure higher frequency FH and lower frequency FL. Here we have the cursor set for the higher frequency and we get it approximately 4 kHz. Similarly, we can measure the frequency for FL and it will be approximately 2 kHz. We have the cursor set for measuring FL and here we can see it, that FL is equal to 2 kHz. In this experiment, we have to compare the signal to noise ratio at the input and at the output. So at the input, we will add the noise of 1 volt as a reference. 1 volt as a reference. To generate the noise of 1 volt, we'll first set the noise as 1 volt. After setting the noise at 1 volt, we'll give the noise to adder. and the FSK output to the adder. And check the distorted FSK signal at the output of adder. Here we can see the distorted FSK signal. Now we'll see the receiver for FSK. The distorted FSK output will be given as an input to the receiver. Check the data output. It will be same as the data bit stream given in the input. Now we'll see the data output, which should be ideally same as the pattern generator input. For the receiver part, kindly note that the frequency knob should be at minimum. Here we show there is data received. Check the bit duration and the amplitude. This is the final stage to calculate the output SNR. Connect the phase comparator output to the input. Check the noise voltage. Now check the signal voltage. Now when we have the signal voltage and noise voltage, we can calculate the output SNR.